Okay, Assalamualaikum. So, in this video, we will talk about Orb SLAM. Orb stands for Oriented Fast and Rotated Brief. Just like fast, surf, shift, Orb is like another feature that can be extracted from the keyframe. And SLAM obviously simultaneous localization and mapping. Or stand for oriented fast. It means it has done something to like normal fast feature. It has made the fast feature, you can say, invariant to viewpoint and scale changes. Similarly, rotated brief is another feature that deals in intensity values. So, utilizing fast and brief, they have made another feature that is invariant to viewpoints and scale changes. And that all feature is utilized in SLAM, in mapping and localization. It is built on p-time and bag of word. Place recognition is done by bag of word, and localization and mapping phenomena is almost like p-time, parallel tracking and localization. Again, obviously, it includes loop closure. It will detect whether robot has come to the previously visited place and it is the closing point and the loop is closed. It can detect that, and obviously it allows the invariant images. Why they used orb? First thing, obviously, they probably would have compared different features and they have utilized this one. Why? Because this can be helping them to make like their system, the whole model, invariant to viewpoint and scale change. Secondly, orb can be easily extracted. Okay? Like it can be extracted in just 33 milliseconds, unlike shift and search that takes around 300 milliseconds. So by this thing, this Orb SLAM is now real time. It can be utilized in real time. It can be utilized in video, not only like frame. A moving robot can maintain tracking and mapping. Now it is a real time. Overview of the Orb SLAM is like this. Okay, just look for this flow and then I will demonstrate each and every step. Okay, so what will happen? A frame will come and orb features will be extracted from the frame. A robot was moving, it clicked first. Let's say a first frame came and orb features were extracted. And when the orb features were extracted, map initialization began. And how they initialize map? Obviously to find relative pose between two consecutive frames. They are obviously not the pose cannot be initialized with only one frame. It needs at least two frames. So when you have two frames, you can initialize map. Then initial pose estimation. Obviously, between two frames, you can find the pose. Then tracking begins. Track the local map. Obviously, the robot hasn't visited the whole area yet, so it will start building the local map. The map of the area it has recently seen, local map, and here it starts making map points around the region. Okay, map points are usually where like Orb SLAM has extracted some features, and in this case, obviously all features. So, what does map point possess in Orb SLAM? And a map point has x, like its 3D coordinates. A map point has these things. First, it knows the exact 3D location in the environment. Secondly, a map point knows viewing direction, or it has the viewing direction, okay, from where it has been observed, or how will it look like when it is observed from multiple directions. So it has this feature as well. It has viewing direction. It will be a unit vector. Secondly, it will know orb descriptors with the least Hamming distance obviously the map point will be detected where there was a orb feature in the keyframe. So the map point will know the information of that particular orb feature with least Hamming distance that was most similar to the 3D point. You can search on it how you can find the Hamming distance. Like, it's not a big deal. The whole idea of finding the distance between the point and the feature is to like make this thing sure that this is the most responsible feature for my existence, like for map point's existence. Then it has these two values, d max and d min, okay, to from how long from the 3D point the point can be visible. This is called d max. For example, it is detected, a map point is detected here. Now, from how long or from how much far away this point can be visible, this is called d max. And similarly, d min is from like how much near to the map point a robot should go so that it is visible. Obviously, there is a least distance as well as a max distance. Okay, so this is the map point. Now frame came. Now you have to decide whether next frame came, and now you have to decide whether the keyframe, whether the new frame can be considered as a keyframe or not. If okay, how can you decide whether it is a keyframe or not? Obviously, there are certain parameters of judging that as well. We will see it later. Now, keyframe, and then what is similarly to the map point, what will or what information will keyframe possess? It will know the camera pose, which is TW. It will know camera intrinsics and focal length and principal point, and similarly it will know all the orb features that were extracted from the that particular keyframe. All the keyframe, not only those that were responsible for building the map points, all the keyframes that were like extracted and that were not distorted. Okay, now you have found that it is a keyframe. It can be inserted in your keyframe database. Now keyframe is inserted. Recent map point current. Now in Orb SLAM, keyframes are usually collected at a generous policy. Like at start, whatever type of map point it is, or like the criteria is very low, you can like consider any point as a map point and start. But later in the stage, the map points as well as the keyframes can be culled, can be cancelled, can be deleted. So when the whole process begins, the keyframe and map points are being collected at a generous policy, but later in this stage these are culled. So what will happen? It will cull out the recent map points. On which criteria? This one. If the points are visible in at least 25%, if the map points are visible at least 25% of frames, not keyframes, at 25% of frames where it was predicted to be visible, then you will consider this point, like you will not cull that point. Plus, must be observed in at least 3 keyframes, consecutive 3 keyframes. It must be visible. If a map point has these 2 properties, you will consider that map point. Otherwise, you will cull it, you will delete it. Now, secondly, new point creation. When a new keyframe is coming, obviously it will be coming with different orb features. Like it will be coming with observation of new environment. So you will add new features or new map points. Then local bundle adjustment. After that, you will do bundle adjustment. Bundle adjustment is same, like you minimize the reprojection error. You refine your local map. Then local keyframe culling. Similarly, as you know, you were collecting at generous policy keyframes. Now you need to cull some. So when you will cull the keyframe or delete it, discard if 90% map points are visible in 3 other keyframes at same or finer scale. If the if the 90% map points associated with that keyframe are visible in 3 other keyframes at same or finer scale, you will like downscale it the same way you like you did it in, I guess, p time. Criteria is a bit different, but downscaling is done, or maybe it is based upon p time, so it can be downscaling it like it was done in p time. So if it is visible, if the map points associated with that particular keyframe are visible in 3 other keyframes and at same or finer scale, then you will discard the keyframe. Why? Because it is unnecessary. You have the same information there already. Local keyframe calling. Now, candidate detection. Now it will detect whether the new keyframe is a loop closure, responsible for the loop closure or not. So a candidate for that particular keyframe is detected from the database. Obviously it is done the same way it is done in PTAM. Like whole process is different, we will talk about that. But obviously PTAM was not scale or viewpoint invariant, but this is invariant, so there will be some difference. Okay, so candidate detection, and then compute sim3 is computed. Now sim3 is a group, a more refined one than SC3 group, and it is responsible for transformation in scale and viewpoint invariant situation. For example, a robot moves in a circle. It detected this dustbin. If it is not visible, obviously there is a dustbin, believe me. Okay, so the dustbin, and robot visited saw this in observation in, let's say, its first keyframe, and then it moved and it completed the circle, and again the same features came, or the same dustbin appeared, but this time it was on different scale and different viewpoints. So it is very brilliant thing in Orb SLAM that it can easily detect whether the same frame has already been visited or not. This thing is called, to make this thing sure, you need to perform the scale and viewpoint invariant transformation between the first keyframe and the new keyframe that is now we are saying is a loop closure. So that thing is done in sim3. Okay, you will compute sim3 and you will decide, oh, now this is the loop closure, and then obviously you will perform loop correction, like you will fuse the map loop, you will like close the map, not you, obviously the whole system. Then you will optimize the essential graph. Now what is essential graph? First we will start with covisibility graph. In covisibility graph, obviously, so in graph there are nodes and there are edges. Okay, just like this, there are nodes and then there are edges. These are nodes and these are edges. So each node here in this covisibility graph define or represent a keyframe, and the distance between the keyframe represents how much it was similar, or let me put it in a simple way. In this keyframe, if this keyframe and this keyframe both has at least 15 map points common, then you will develop an edge between it in covisibility graph. So this keyframe and this keyframe, edge will be there if in both keyframes 15 map points, at least 15 map points are visible, and 15 are like so minimum amount. It can be easily visible between the different keyframes. So therefore, as the criteria is very low, this graph will be so dense, there will be a lot of edges, because 15 map points are easily visible between many keyframes, especially if the robot is not moving with like a great velocity. Similarly, then we have essential graph. In essential graph, nodes are same, like nodes are represented by keyframe, and there will be equal number of nodes in essential graph and covariability graph. But edges will decrease because you have like increased the criteria. So what is the criteria? Now you will develop an edge between two keyframes or two nodes when there are at least 100 map points visible between the two. Obviously, you can know now this graph will be sparse. This will not be dense. Okay, you like the, it should save at least, it should save like same amount of information that was there, but with less edges. And then there is spanning tree that has the least number of edges. Okay, but still trying to save the same amount of information. So it has the most number of edges, it has like lesser than that, and it has least number of edges. So it will be the most sparse graph. So in Orb SLAM they are making these graphs as well. So at the end, when they have done the loop closure, they will optimize their essential graph. They will see if everything was going fine, and if after loop closing any optimization is needed, any refinement to the essential graph is needed, they will do that. Now this is a bit tricky part. I will make a video on candidate detection and loop closure, inshallah. So this was all about Orb SLAM. See you in the next video.